We're back. This is a Middle Perch live on the internet. I am MTK on the MIC. Did a little painting this morning. We're going to read some consilience this afternoon. I thought I'd check back in. There's some decision making like crazy going on this piece, which implies that it might be able to be finished very, very soon, which I think would be exciting. So I might be working on that as we go along. So what's interesting about this is I should say what's not interesting about this is the bottom television. That is not necessarily decided yet. Top two look good. Trim a little bit of the bottom off of this. So I went ahead and cut this thing. That's a big deal to me. This was in the newspaper in the San Francisco Chronicle in 2008. So this piece of paper is 11 years old, right? Those are the tankers and container ship that I took out of. What's cool about this one particular segment is look, it has a trawler, a container ship, and 4 oil tankers, which is sweet. So that has made its way into this, and it's just right. Oh my God, it's so pretty. It's countering the very bright bridge piece in a magnificent way. So quite pleased. Now we have only left the bottom television set, which is going to be trickier. Again, we're talking about composition now from the standpoint of conceptualization. If I'm taking a long time to make something, it's because I'm thinking about it for a long time. If I'm thinking about it for a long time, I've already run through a lot of what the viewer sees when they go to see it, right? So one of the objectives is to create depth of field that is enduring. So if you walk up to the piece, you see something and you go, oh yeah, that's what that is. And then you stop looking, and then you look again, you go, oh wait, no, oh wait, no, oh wait, no, oh wait. And then you have a more enduring experience. And there's tactical ways one can do that. You can see that piece, for example, the one that I think nobody understands because they think it's just a woman walking into the ocean. You have to kind of spend some time with it to grasp all of what's happening there. And my approach is tactical. It's not accidental, because I run through millions of possibilities and then make decisions. And then when it comes time to glue, that's the finale, so you don't get to do it twice. And when I glue, I'm very confident because of that. I've thought about it already. I already run through a million things. This was a quick decision, it looks like to you probably now. To cut this piece of paper, pull out the middle section and put it right there is something that for 11 years I didn't know needed to happen till right now. Could use some shaping. And the shape of California is definitely the subtext here. It's just too too harsh of an angle is the problem. This thing needs to be curved right there. Yeah, I can do the same up top, very slightly. Yeah, that'll do it. Oh, that's beautiful, guys. That's what I want. Okay, now the bottom television, either it's a 0, which is possible. A single white dot in the center with this blue border would really imply sweetly a television going off. And I could white line it too. But I don't know if that communicates anything. That it communicates negation. It communicates that the device itself is off. It implies the vacuum tube technology, the warm little glowing light that then fades out. That, I think, is what I like about it. Yeah, I think that's the reason to do that. It's just impossible to visualize without the main element. It's so hard to do, man. That's crazy. All right, let me see if I can add that. Man, it's looking really good. Okay, so let's give that a rest. That was a good session. A lot happened. That's not normal when a lot happens. So that's a good session. And we can move this out of the way. Art. That is going to be a nice looking piece when it's finished. I can see it being finished very soon. But that is not what we're going to do right now. What we're going to do right now is the next chapter of Consilience, which we do every... When do we do it? I love that. As if there's any kind of schedule. There's no schedule at A Middle Perch live on the internet with your host. I'm MTK on the MIC. Have I said that already in this app? I don't know. I was trying to get this to be over here and the little guy to be on the corner underneath it. I feel like that should do it. Think that'll do it? I love that it's physical. Although I don't see me going on Twitter anytime soon. It annoys me every single time I'm on it. Yeah, lately. So, I think that's a bailing deal for a while. So we're doing Consilience, which we do dry. Let's check the chapter we're on while we're at it. This is Chupacabra. I like this one. And Consilience by Edward O. Wilson. We are on Chapter 5, Part 3. Chapter 5, Part 3, Chapter 5, Part 3. Chapter 5 is Ariadne's thread. If you'll remember, this is the thread used to trace your way back out of the maze, the labyrinth. Whoa! Look now, that's me saying it. Off, please. Thank you. Boy, that was weird. Okay. So, consilience, we're going to read consilience as we do. Ariadne's thread, the metaphor for the way knowledge is kind of... Well, anyway, you can listen to the previous 11:15, 11:16. We're going to pick this up. Ariadne's thread, Part 3. What does complexity theory need to be successful in biology? Complexity theory needs more empirical information. Biology can supply it. 300 years in the making, having recently been wedded to physics and chemistry, biology is now a mature science. But its researchers may not require a body of special theory to master complexity. They have refined reductionism into a high art and begun to achieve partial synthesis at the level of the molecule and the organelle. And even if complete cells and organisms are still beyond them, they know they can reconstruct some of the elements one at a time. They foresee no need for overarching grand explanations as a prerequisite for creating artificial life. An organism is a machine, and the laws of physics and chemistry, most believe, are enough to do the job, given sufficient time and research funding. Putting a living cell together will be a moonshot, not an Einsteinian revolution of space and time. Complexity in real organisms is being taken apart swiftly enough to enliven the pages of Nature and Science magazines, he means, each week, and drain away the need for conceptual revolution. A great vaulting revolution may occur, and suddenly, but the busy and well-fed masses of researchers are not awaiting it in desperate suspense. Okay, so this is, remember, being written in 1998. And, we had the Chinese fellow with the babies this last year, and so much has happened since 1998. So let's just take this for what it is. The machine the biologists have opened up is a creation of riveting beauty. At its heart are the nucleic acid codes, which in a typical vertebrate animal may comprise about 50,000 to 100,000 genes. Each gene is a string of 2,000 to 3,000 base pairs, genetic letters. Among the base pairs composing active genes, each triplet, set of 3, translates into an amino acid. The final molecular products of the genes, as transcribed outward through the cell by scores of perfectly orchestrated chemical reactions, are sequences of amino acids folded into giant protein molecules. There are about 100,000 kinds of protein in a vertebrate animal. Where the nucleic acids are the codes, the proteins are the substance of life, making up half the animal's dry weight. They give form to the body, hold it together by collagen sinews, move it by muscle, catalyze all its animating chemical reactions, transport oxygen to all its parts, arm the immune system, and carry the signals by which the brain scans the environment and mediates behavior. The role a protein molecule plays is determined not just by its primary structure, not just by the sequence of amino acids within it, but also by its shape. The amino acid string of each kind is folded upon itself in a precise manner, coiled about like twine and crumpled together like a piece of wadded paper. The total molecule bears resemblance to forms as variable as clouds in the sky. Looking at these forms, we readily imagine lumpy spheres, donuts, dumbbells, rams' heads, angels with wings spread, and corkscrews. The resulting contours of the surface are particularly critical for the function of enzymes, the proteins that catalyze the body's chemistry. Somewhere on the surface is the active site, a pocket or groove consisting of a few of the amino acids, held in place by the architecture of the remaining amino acids. Only substrate molecules of a very specific form can fit the active site and submit to catalysis. As one docks in the correct alignments, its active site alters shape slightly. The two molecules bind more closely, like hands clasped in greeting. Within an instant, the substrate molecule is changed chemically and released. In the embrace of the enzyme sucrase, for example, sucrose is cleaved into fructose and glucose. Just as swiftly, the active site of the enzyme molecule returns to its original shape, with its chemical structure unchanged. The productivity of most types of enzyme molecules snapping in and out of the active state is prodigious. A single one can process 1,000 substrate molecules every second. How to put all these nanometer components and millisecond reactions together into a coherent picture? Biologists are determined to do it from the ground up, molecule by molecule, and metabolic pathway by metabolic pathway. They have begun to assemble the data and mathematical tools needed to model an entire cell. When they succeed, they will also have reached the level of entire simple organisms, the single-cell bacteria, archaea, and protists. Most biologists favor middle-level models in their theory of cell integration, neither primarily mathematical nor purely descriptive, but instead front-loaded with large amounts of empirical information and conceived as genetic networks. The flavor of this state-of-the-art approach has been nicely captured by two of the researchers, William Loomis and Paul Sternberg, as follows, quote, "The nodes of such networks are genes, or their RNA and protein products. The connections are the regulatory and physical interactions among the RNAs, proteins, and cis-regulatory DNA sequences of each gene. Modern molecular genetic techniques have greatly increased the rate at which genes are being recognized and their primary sequences determined. The challenge is to link the genes and their products into functional pathways, circuits, and networks. Analyses of regulatory networks, such as those involving signal transduction and transcriptional regulation cascades, illustrate combinatorial action that implements, for example, digital logic, analog digital conversions, crosstalk and insulation, and signal integration. Although the existence of sophisticated network elements has been suggested by decades of physiological studies, what is new is the scale and detail becoming available for the components. Much of current molecular biology focuses on identifying new components, defining the regulatory inputs and outputs of each node, and delineating the physiologically relevant pathways." Close quote. The complexity conceived in this single paragraph exceeds that in supercomputers, million-part space vehicles, and all the other artifacts of human technology. Can scientists manage to explain it, and in a microscopic system to boot? The answer is undoubtedly yes. Yes, for social reasons, if no other. Scientists have been charged with conquering cancer, genetic disease, and viral infection, all of which are cellular disorders, and they are massively funded to accomplish these tasks. They know roughly the way to reach the goals demanded by the public, and they will not fail. Science, like art, and as always through history, follows patronage. Rapidly improving instrumentation already allows biologists to probe the interior of living cells and inspect the molecular architecture directly. They are discovering some of the simplicities by which adaptive systems organize themselves. Among the notable simplicities are the rules used to fold the flexuous strings of amino acids into serviceable shapes of protein molecules, and the powered filtering devices by which membranes admit selected substances in and out of the cell and organelles. Scientists are also acquiring the computational capacity needed to simulate these and even more complex processes. In 1995, an American team using two linked Intel Paragon computers set a world speed record of 281 billion calculations per second. I'm sure we've exceeded that by so much now. The U.S. Federal High Performance Program has upped the goal to a trillion calculations per second by the end of the century. That's already passed, obviously. By the year 2020, that's next year, folks, peta crunchers capable of reaching 1,000 trillion calculations per second may be possible, although new technologies and programming methods will be needed to reach that level. At this point, brute force simulation of cell mechanics, tracking every active molecule and its web of interactions, should be attainable, even without the simplifying principles envisioned in complexity theory. Scientists also foresee early solutions to the self-assembly of finished cells into tissues and whole multicellular organisms. In 1994, the editors of Science magazine celebrated the inauguration of developmental biology by Wilhelm Roux a century earlier, asked 100 contemporary researchers in the field to identify what they considered the crucial unanswered questions in the discipline. Their responses, in rank order of attributed importance, were, this is in 1994, 1. The molecular mechanisms of tissue and organ development. 2. The connection between development and genetic evolution. 3. The steps by which cells become committed to a particular fate. 4. The role of cell-to-cell signaling in tissue development. 5. The self-assembly of tissue patterns in the early embryo. 6. The manner in which nerve cells establish their specific connections to create the nerve cord and brain. 7. The means by which cells choose to divide and to die in the sculpting of tissues and organs. 8. The steps by which the processes controlling transcription, the transmission of DNA information within the cell, affect the differentiation of tissues and organs. So this was in 1994. Remarkably, the biologists considered research on all these topics to be in a state of rapid advance, with partial success in at least some of them close at hand. So my guess is in the 20 years since this, we've had some success in that. Let us suppose that early in the next century, he means now, the hopes of the molecular and cellular biologists are fully realized. Suppose further that the researchers succeed in breaking a human cell down into all of its component parts, track the processes, and accurately model the whole system from the molecules up. And suppose finally that the developmental biologists whose focus is on tissues and organs enjoy similar success. The stage will then be set for the final assault on the still more complex systems of mind and behavior. They are, after all, products of the self-same kinds of molecules, tissues, and organs. Let us see how such explanatory power might be acquired. With a close approximation of organic processes in a few species completed, it will be possible to infer how life is reproduced and maintained in an indefinite number of other species. With such an expansion of comparative holistic biology, a picture could be drawn of life as it is today, as it also was in the earliest stages of its evolution, and as it might be on other planets with different but habitable environments. In visualizing habitable environments, we will need to be liberal, keeping in mind that algae grow up within rocks in Antarctica, and microorganisms thrive in the boiling water of a deep-sea thermal vent. At some point, deep and powerful principles of complexity may well emerge from the large ensemble of simulations. They will reveal the algorithms conserved across many levels of organization up to the most complex systems conceivable. These systems will be self-assembled, sustainable, and constantly changing yet perfectly reproducing. In other words, they will be living organisms. At this time, if it comes, and I believe it will come, we will have a true theory of biology, as opposed to thick descriptions of particular living processes that now constitute the science. Its principles will accelerate inquiry into mind, behavior, and ecosystems, which are products of organisms, and by virtue of their extreme complexity, the ultimate challenge. So the important questions are: first, do general organizing principles exist that allow a living organism to be reconstituted in full without recourse to brute force simulation of all its molecules and atoms? Second, will the same principles apply to mind, behavior, and ecosystems? Third, is there a body of mathematics that will serve as a natural language for biology, parallel to the one that works so well for physics? Fourth, even if the correct principles are discovered, how detailed must factual information be in order to use those principles in the desired models? In all these matters, we see today as through a glass, darkly. In time, to complete the biblical illusion, we will come face to face with it all, and perhaps see it clearly. In any case, the search for answers will test the full powers of the human intellect. That's the end of chapter 5. Ariadne's Thread, from Consilience by E.O. Wilson. Thanks for joining me.